I'd like to finish up the Module 3 part of this class on three-phase transformers by adding this extra appendix to the lecture number 6 within that module on three-phase circuits, and in particular discuss the use of an equivalent line to neutral circuit in order to analyze three-phase transformer problems. So let's just start by reminding ourselves of the usefulness of the equivalent line to neutral circuit, or the equivalent single-phase circuit. We could call it that as well, but it's probably better to refer to it as a line to neutral circuit for the reasons that will become clear as I go through this. And it's easy to start by just looking at the Wye-Wye transformer configuration. So if we're looking at a three-phase transformer as a system, the way that we are right now, we have a set of three-phase windings on the primary, and label the terminals to that primary winding. So you've got an A1 terminal, a B1 terminal, and a C1 terminal. And then on the secondary side, you would have an A2 terminal, B2 terminal, and C2 terminal. One of the main reasons for transformers, other than simply stepping up or stepping down the voltages, or actually in addition to that, is to isolate the grounding systems for two parts of a larger system. That means that the references of those systems are isolated from each other. In fact, the neutral references are. So then it would be appropriate to identify a neutral for the primary side and a neutral for the secondary side. Now, we had first introduced three-phase circuits, and we showed that if you had a three-phase source connected to a three-phase load, there was a neutral at each end, that effectively those neutrals were connected to each other. In this case, the neutrals form a separate reference on each side of the transformer and effectively allow us to break the circuit up into three pieces if we wanted, per each side of the transformer, or analyze an individual line to neutral circuit on the primary and on the secondary side. We could very easily convince ourselves that we can analyze this single line to neutral circuit for phase A, and whatever we get on that phase from the standpoint of a balanced system and understanding the voltages and currents that might be applied to a load or coming from a source connected to this transformer, we could figure those out for one line to neutral on each side of the transformer, and then we could simply adjust our final answer by multiplying by the appropriate factors of 3 and square root of 3 to get the full system, say, power, input or load power, and so on. So it makes this is quite an easy problem to solve. To illustrate what I'm talking about, I have this single-phase equivalent circuit for the transformer. And if we were to look at the three-phase transformer, we would typically identify the step-down or step-down capability of this transformer by specifying the line-to-line voltages on the primary side and the line-to-line voltages on the secondary side, as opposed to a turns ratio, which is what I would have here in this single-phase transformer circuit. That turns ratio is definitely there, and it's associated with the single-phase winding right here, that part of the circuit. So I can just analyze one of the phases, and what I learn on this phase applies to all three phases equally. So I have initially a system where there's a line-to-line voltage on the primary side, the actual line-to-line voltage, and there's an actual line-to-line voltage on the secondary side. Now these voltages are a function of whatever the upstream voltage is that we are applying to the transformer. They're not the same as this. This is a transformer voltage ratio that's fixed according to the transformer rating. So I can, because I know these line-to-line values on each side, I can define a line to neutral on the primary and a line to neutral on the secondary. There are line currents coming in on the primary side and going out on the secondary side. The nice thing about it is that these line currents are the same as the phase currents. So the drawing that I have shown right below here is a drawing of the transformer phases. So this would be the terminal for this transformer. Let's say that was A1, and this is the other terminal of the transformer, A2, and I'm applying a voltage to the primary and I have a load on the secondary. The phase voltage is equal on the primary, equal to the line to neutral voltage. So they're really the same thing. On the secondary side, the phase voltage, the actual voltage of the winding, is equal to the line to neutral voltage. The phase current on the primary is equal to the line current on the primary, and the phase current on the secondary is equal to the line current on the secondary. We know that the amplitudes of the voltages that we're talking about here are related between line to line and line to neutral by a factor square root of 3. So V line to line is square root of 3 times V line to neutral. Or we could say that the V line to neutral on either side is equal to whatever the V line to line is divided by square root of 3. So whenever we're looking at a line to neutral circuit, this is true. We happen to be lucky in this case with the Wye-Wye configuration to have the phase voltages on both sides also being equal to the line to neutral voltage, and the phase currents on either side being equal to the line currents. But this will not always be the case. And so the point of this lecture is to really point out that depending on the transformer winding connections, whether it's Wye-Wye or Wye-Delta, Delta-Wye or Delta-Delta, these relationships will be different. They are exactly this in the case of the Wye-Wye connection. So we look at our equivalent phase circuit. Here are the equivalent phase impedances. We have the R1. We've got the leakage of the primary, XL1. We have the leakage of the secondary, XL2. and the resistance of the secondary R2. We've got the phase current here, and what I'm going to be doing now for each of these scenarios is we're going to analyze them as a line to neutral circuit. And so once I decide that I have a line to neutral circuit, I'm just dealing with primary and secondary voltages and currents. So the primary current is I1, the primary voltage is V1, the secondary current is I2, and the secondary voltage at the terminals is V2. And these voltages are all with respect to the neutral points. Everything now that we learned with single-phase transformers applies to this circuit. And so if, for example, I had a problem like this, let's give an actual numerical example and show you the process at least. Oh, and I also mentioned that we have the magnetizing reactance and the core loss resistance as well. This is the full detailed circuit. In the prior part of this lecture, I showed how you could even simplify the circuit by ignoring those branch impedances, but I've got them in here to really give you the full picture of what's going on. Okay, so I have given to me, in this case, the volt amperes at the load, the line-to-line voltage at the load, and the power factor at the load. And I'm asked to find the volt amperes at the source, or on the primary side, the line-to-line voltage and the primary and the power factor. So the step-by-step approach here would be to first find the line current at the load. That line current will be the line current here, IL2, that's going out to the load. Notice I'm not showing sources and loads here, but I'm talking about connecting a source to this side and a load over to this side. So the first thing is, if I know the V line to line and I know the S, step one, the I line current is going to be equal to S divided by square root of 3 V line to line. And these are all load or primary or secondary side quantities. And next I want to find the current I2. So I2 is equal to the line current and I know, if I know the power factor, I need to know whether it's leading or lagging. And recall that I put this little K here, so that K is 1 if leading, it's -1 if lagging, times the inverse cosine of the power factor. So now I have the magnitude and phase of the secondary side current. The next thing that I would need to do, the best step to take is to find out how things are reflecting onto the primary side, or what is the primary side current here. Now, with this detailed circuit that we're showing here, I'm assuming that we know all of these quantities. So we know these quantities here. And this current I2 reflected to the primary side, it would be right here. So that would be I2 prime in the equivalent circuit. So I really have a simplified circuit now that looks like this. And I've now found I2 prime. And I2 prime, the best way to find I2 prime is to say that, to treat it like an equivalent line current. So coming back to this, that this, whatever current is coming out of this magnetizing branch is the same as the line current. Now the only way I can do that, so this, I'm talking about this current right here, is to have this line to neutral configuration, which I don't have to do anything special because I already have it in that form. And what I mean by that is that I can now say that I2 prime is equal to I2 times the inverse of the line-to-line voltage ratio, which is related to the turns ratio, and we went through this at the beginning part of this lecture, that I'm going to use this to find I2 prime. So that's step 3. Again, I want to remind everyone that everything that I'm showing here in green is given in solving this circuit. We haven't talked about the voltage here. This is the load. We could have derived that impedance from what we were given if we wanted, but let's instead use the voltage like the other transformer problems that we've been solving, the single-phase transformer problems. And we're going to say this voltage, it's right at the terminals of the transformer, is V2 prime. And so we really are going to, in step 4, set up to solve for the primary side quantities. To do that, we need to know V2 prime. So what is V2 prime? Well, if we look at what we were given the line-to-line voltage on the secondary. And I'm just going to clean up a little bit, being a little bit anal here. What am I given? I'll make it green, okay? So these are the quantities I was given. And I would have also been given this information here. What is this, right? And then the rest of this stuff is what I'm deriving. So now what I have is I have the V2 prime. That's a phasor. It's going to be equal, because I've defined the power factor at the load, and it's right at the terminals of the transformer. That may not be the case, and we have to always pay attention to that. But the V2 prime is going to be the given line-to-line voltage at the secondary that I was given at the load side, divided by square root of 3, but then I have to move it to the other side of the transformer by the transformer ratio, voltage ratio, which is V line-to-line 1 over V line to line 2. And it's referenced at 0 degrees. So I really have everything now on the secondary side of my equivalent circuit. I've got everything I need to know here, and I just need to solve for the other quantities. So the next step would be use current division to find to find I1, or if XM is nearly infinity, very big, and RC, which is what would be the case if they weren't given to you, then I already know I1 is approximately equal to I2 prime. And then from there, once we know I1, we can finish off the problem here. And we can calculate the primary line to neutral voltage. And finally, once we know the primary line to neutral voltage, V line to line on the primary side is equal to the magnitude of the primary voltage times square root of 3. So don't forget to put that square root of 3 back in. And then I have to find the input power factor. So there's a lot of ways to do it, but you were also, in this case, we were asked, so I go back up to here, to find this, right? So probably the most straightforward way for me to solve this problem right now, I have actually found everything here with V1. So since we're using the S to find everything, we can't forget that this is a three-phase circuit, so we've got to put a 3 right here, multiply that, times V1 times the conjugate of I1. The magnitude of S is the S that we're asked to find, and the angle, the negative of that angle of S, that's the power factor angle on the primary side, or you could say the input side power factor angle, and we will know if it's leading or lagging. And so we can then take the cosine and find the power factor. And the leading or lagging will define the sine, or essentially I can put this k here, which is a 1 or a -1. So there's our answer to the 3 things we were asked for. Now this is quite straightforward. We did this for a line to neutral circuit. So to review, what we did was we had a N1 and an N2 here, and now when we make this equivalent circuit referring everything to the primary, this is N here, so N1 is really kind of equal to an N2 prime, really moved over to that side. And then we just do what we've always done. So the key and the trick to everything is for us to get to the line to neutral circuit Now I'm going to show you the approach for a delta Y, for a Y-delta circuit. So the Y-delta circuit looks like this, and for a delta-delta circuit. So we're going to go through these two circuits right here and show the same approach. And then you pretty much have everything you need to know, or the methodology, and we will give one example, and then the rest is simply practice. So now let's consider this Y to delta transformer. We've got it set up here. The primary side is like it was before. We've got this. The phase circuit here is also the same as the line to neutral circuit. So we've got an N1 here. We've given the transformer has our line-to-line voltage quantity, usually given, and then that's a rating. This is the actual voltage, the V line to neutral on the primary side, and the actual V line to line on the primary side, the I line 1 coming into this, and then the current going into the phase, that would be I phase 1. I'm going to separate these just a little bit to make some room. Pretty straightforward as before. We know that the V line to neutral on the primary side is equal to V line to line 1 divided by square root of 3. These are magnitudes we're talking about, of course. The I, and go back to this, that's also equal to the phase voltage, V phase 1, across the phase winding. The I line 1 is the same as the phase current, I phase 1. If we were to draw an equivalent line to neutral circuit, we could quite easily come up with all of these quantities the same way we did before. And we could solve a problem if we were to assume, like I've kind of indicated here, that these parameters were all given. Now the issue is on the delta side. What are we going to do there? Well, if we look on the delta side, we have a phase voltage here. It's a little easier. This would be the exact correlating, the way these symbols go, phase voltage to the primary side. That would be the equivalent phase A voltage of the transformer. But it's a little easier to see if we consider this, because this is from A, this is actually A, C to A voltage. And I've got the arrow pointing in the wrong direction. It's a little easier for us to think about the AB voltage here, because we can see these lines coming in here. So we've got V line to line 1, and that actually is equal to V line to line 2. That's equal to V phase 2. So on the secondary side, V phase 2 equals V line to line 2. It does not equal V line to neutral 2. That is a different voltage. We know clearly that the phase current then, if we were going to say this was the current through that phase, I phase 2 here, in the B phase, B winding, corresponding to this winding right here, that it's smaller than the line current I line 2. By the magnitude would be smaller by factor square root of 3. So I phase 2 would, the magnitude of that, let's say it was a phasor to be completely exact, would be equal to the quantity I line 2 divided by square root of 3. Now the what we don't know is what is the line to neutral voltage. Where is the neutral? There's no physical place that it can be connected, but I can put it effectively right here in the middle and call that N2. So it's a virtual voltage measurement. And now I could try not to run into things here. This could be the V line to neutral 2 right here, from A to neutral, or B to neutral would be there. C to neutral would be there. Draw it a little better. Think about these as voltage measurement points. And this is V line to neutral 2 right there. So that's what we need to do to find an equivalent line to neutral circuit. So first of all, we're trying to get this line to neutral circuit that looks like this. Where this would be the phasor voltage V2. We want to find the I2 here. Well, we can, let's say that we know something about the impedance or the load impedance that this transformer is feeding. We can just establish this to be our reference. We know the magnitude, so we know that V2 is going to be equal to V line to line 2 divided by square root of 3. And we can just say, let's reference that at 0. So I2 would end up being I line 2 with our equivalent line to neutral circuit. And then it would be an angle. And we could say, well, if we knew the load power factor right there, we could say that's the power factor angle. Or if we don't, let's say we know the load impedance, we could say it's the negative of the impedance angle. And let's check this idea. If we know that, let's just check it in terms of the power calculation. So for the three-phase circuit, the total power S, and I'm just going to talk about it in terms of magnitude, would be 3 times V phase times I phase. In order for our line to neutral circuit to work, that power would have to be also 3 times V line to neutral times what we're saying is the I line. So let's check ourselves here. V phase is equal to V line to line. I phase equals I line divided by square root of 3. And so the S, plugging those values in, ends up becoming 3 times V line to line times I line divided by square root of 3, or square root of 3 V line to line I line. So this is holding true. We know that's always going to be true. Let's check it with our line to neutral circuit. In our line to neutral circuit, the V line to neutral is equal to V line to line divided by square root of 3. And the I of that circuit, it has to be the line current. A little bit redundant there, but we're really saying that I phase is the line current in our equivalent line to neutral, and that by saying that, that means that we are able to say I've got this neutral point right here. So then that this current here has to be the line current. So what is the S? The S would be 3 times each line to neutral power. This is again just amplitudes or volt amperes, so it'd be 3 times V line to line divided by square root of 3 times I line, or square root of 3 V line to line I line. So we've checked it and this works. And so the only other thing we need to think about is, we go back here, we have a turns ratio, and we're using our line to neutral circuit to define our turns ratio. Turns ratio is always going to be the ratio of the primary voltage to the secondary voltage. So the primary voltage in our equivalent line to neutral circuit is V line to line 1 divided by square root of 3. And the secondary voltage, or V2, on our line to neutral circuit is V line to line 2 divided by square root of 3. So A equals V line to line 1 over V line to line 2. So this is very helpful because it tells us why, another way of looking at how useful it is to express things this way. What we're really saying too is that this is for each line to neutral phase, and it may not be physically realizable. It won't be if there's a delta, but it's going to be A to 1 still, where A equals the ratios of these. And that would also mean that I could transform the current here over to that current there using that same ratio. This is something that's not really clearly spelled out in the textbook, but I'm just trying to emphasize it here. It's a common mistake that's made on exams to miss this, to just overthink this problem too much. Okay, so we actually have it. So now there's one more relationship. Recall in Module 1 we learned about impedances. And our whole goal is that we're trying to get ourselves, we're trying to get to a Y circuit, because that's what we can analyze. That's a line to neutral circuit. So ZY, remember, is equal to Z delta divided by 3. So if I had given all of these parameters before, this is going to our equivalent circuit here. I've got R1, JXL1 here, JXM, RC. On the other side, we were given JXL2, but now because we had to transform it into a Y circuit, we have to divide it by 3. And the same thing goes for the resistance R2. So any impedance of a delta has to be divided by 3 in order to get it into this equivalent Y. And we've got the N1 here, and we've got the N2 right here. And we've got the current here, essentially the line current on the 1. Got the line current coming out on the 2. This is our I1. This is our I2. We've got our V2 problem. And then if you were simply to, let's just look, let's try to refer everything just to the primary. And then you could solve it that way, or you might have to go the other way and refer everything to the secondary. then you'd have to have these transformed by that same turns ratio squared, just like we learned before. XL2 prime divided by 3. And this is, let's make these blue, JXL2 prime divided by 3, and R2 prime divided by 3. So we're just carrying the 3 out in these calculations here, and these stay the same. And now we've got the voltages, currents, and there we are. So that's that one, and you've got a single neutral point now reference to work with. Okay, now we can go through this one fairly quickly. What we have now is the Delta transformer. Everything we did on the secondary we now have to do to the primary. So we've got our V line to line 1 here, and the phase voltage is V phase 1 here. We've got V phase 2 here, and we've got the V line to line 2 right here, I line 2, I line 1. There's a phase currents, I phase 2. I realize I don't have my color codes consistent, so let me clean this up a minute here. So I'm not going to make this extremely boring by going through everything again, but really what you're going to end up having is these factor of 3's end up on the other side as well, because it was a delta-delta. Everything else we went through is going to apply. The V1 is equal to V line to line 1 divided by square root of 3. Whatever the angle is there, depending, like, let's say we could define that as the reference. This is just, you know, we just picked that. Or V2 equals V line to line 2 divided by square root of 3, 0. You got to have either or and work it one way or the other, okay? So, you know, if you have this, then you're going to have the input angle is dependent. If you're going to have this, the output voltage angle is dependent. And you've got the I. These angles are really, depends on what information you've been given as to what you're going to use. It's got to be the I line 1, whatever that angle is, and the I2, whatever that angle is there. So I would recommend that you go do this exercise yourself. Find the delta Y equivalent circuit. Okay, it's a line to neutral circuit. All right, let's do an example. So let's say that you're given a 3-phase feed coming in to a building, And then there's going to be a transformer for that building. So that transformer is, let's say, on the roof or something. It's a local utility fed phase, so it's probably in the 13.8 kV, 60 hertz feed. That's what we're talking about right here. And we have the total building load is S equals 1.5 MVA, 0.85 power factor lagging, we can also say that the transformer, the rooftop transformer, has a rating of S2 MVA. The line-to-line primary rating is 13.8 kilovolts. The line-to-line secondary rating will be 2400 volts. And the transformer is a Wye-Delta. And the last thing that we would need to know is that there is a line feeder impedance of XF equals 0.1 per unit, and the equivalent transformer impedance is 0.07 per unit, or X, we'll call it Z, and it's reactive, so we'll say Z X equals J 0.07, and we'll say this is all based on the primary side transformer ratings. Okay, so we've got this information. Got a three-phase feeder coming in from the utility to feed a load with this total power. We should probably say that the load at this load is at the secondary of the transformer, of the rooftop transformer. So we'll say that V line to line as measured, let's say, equal to 2350 volts. And that's a RMS measurement, and it's a line-to-line measurement. We were given so that's important information. We've got the transformer information, including its impedance, and we have a line feeder. So what could go along with this is a one-line diagram, which I'm going to draw here. There's your feeder coming from the utility. There's the impedance, X feeder. There's your Y delta. And there's your building load right there. there's a measurement of 2350 volts RMS right here coming out of that transformer. The load is S2 MVA, 0.85 aggregate power factor lagging. The transformer is a 13.8 kV to, we can just say 2.4 kV. It has the J.07 per unit impedance, and the feeder is J.1 per unit impedance. And then I say, okay, find the S at the feed. And what I'm kind of saying here is that this feed impedance will be part of the facility here, and the measurement is made right here. So let's find that, and let's find the V line to line at that feed also. So let's see if we can find this problem. We can solve this problem. Okay, so we're going to start going through our steps here. And the first thing we need to do is we need to find the current going here to the load, I line 2. So that I line 2 is equal to the load. Oh, I'm sorry, I wrote this wrong here. That S is 1.5 MVA. Okay. So now we'll find the load current. So it's going to be equal to the S at the load divided by square root of 3 divided by V line to line at the load. That's equal to 1.5 e to the 6 divided by square root of 3 times 2350. And so we get 368.5 amps. Now we know that there's no branch impedances given. These are all series impedances here. So we can actually find the current coming from the feeder on the other side quite easily. I line 1 is going to be equal to I line 2 times what we explained was our virtual line to neutral turns ratio, which is, for current, it would be the inverse ratio of the input and output line to line voltages. So that's actually the ratings of the transformer. So this is V line to line 2 rated over V line to line 1 rated. So the actual answer is 368.5 times the 2.4 kV divided by the primary line to line 13.8. And so we're going to have 64 amps being fed in from the utility grid. Now we really do have to use some equivalent line to neutral circuit to solve the rest of the problem. So we had better, first of all, let's find our base quantities. So we decided to base everything on the transformer. We need to find Z base in order to find the ohmic values of X feeder and Z x. So what we need to do first is we find the s base. That was 2e to the 6. So usually that's volt amperes. Usually when you're given the ratings, you're going to have to do this. Sometimes you might have a problem where it gives you ratings and you don't even use them. That's usually an oversight, or there's a follow-up problem. So pay attention to it, but don't get thrown off by it. The V base, based on the primary side, so that's going to be 13.8 times 10 to the 3 volts divided by square root of 3, which happens to be 7,967. So that's our voltage base. Our I base is S base divided by 3 times V base, 2e to the 6 over 3 times 7,967. So that's 83.7 ohms. And now we can find our ohmic values for the feeder. Feeder reactance, we're neglecting any resistance in the feeder, is equal to J.1 times 83.7, J 8.37. The transformer, the ohmic impedance is J.07 times 83.7, and that is J 5.86. And now let's draw the equivalent line to neutral. And since we're looking for primary side quantities, let's refer it to the primary. So we will have JXF here. It's equal to J 8.37. JZ transformer. That J, let's go back and make this consistent. Impedance of the feeder, impedance of the transformer, J 5.86. We know the current already. The current is, this will be I line 1. That's the same as our primary current, looking into the primary side, I1. We know the magnitude. Maybe we don't even need the phase. Let's just check, because see, I didn't ask for power factor here. So but we do know the magnitude. It's 64 amps. So it's 64 amps, but we don't know what the phase angle is here. We defined our power factor at the load. So we have our V2 prime, and that is 70, and we can find that. So here we have to take the 2350 divide that by square root of 3 to get the line to neutral, and then we have to multiply it times the turns ratio to get it over to the primary side. So that's going to be 13.8 over 2.4. So we can find that it has a reference angle there of 0. And we're really after this. So what I see now is we are going to have the power factor angle to solve this problem. This is the feeder voltage line to neutral right here. What is this angle? Well, there's no branched impedances, and so that angle is the power factor angle. So we know that it's a lagging power factor. So we know that the I1 equals 64. It's negative, lagging, inverse cosine of 0.85. And so that is negative 31.8 degrees. And now we are able to find our line voltage of the feeder. So the V line at the feeder is going to be, we're going to combine these together, so that's going to be 8.37 plus 5.86. We can draw this in phasor form. We know it's got a J, that's a 90, times the phasor form of the current, which is 64, negative 31.8. Then we've got to add the voltage here. So that voltage, multiplying through all of these things right here, is 78.010 degrees. Now here's a check for you. This voltage should look very much like the base voltage for the transformer. It should be close. It is 79.67. Here's another check. This current should not be higher than the base current on the primary side, and it's not. If it was, it'd be overloaded. So we have, now this is assuming, of course, a lagging. You recall that you could have this voltage could be higher if it was a leading power factor. But, you know, we know that we're just going to have a big voltage drop in this system from the feeder. We're going to find out what the feeder voltage is now. And so we can now do the multiplication of these things and simplify this down. Okay, so we've got this expression. Now let's get it into totally in Cartesian form. We've got this. Are we done? No. Because we're really trying to find what we're going to measure at the meter, which is going to be a line-to-line voltage. We're looking for the amplitude of that voltage. So the amplitude of the V line, this is a line to neutral. I don't know why I started calling it V. I screwed up the naming here. 8317. But that isn't our final answer, is it? The V feeder voltage that we're looking for is going to be square root of 3 times that number. And so what is that? It's 14.4 kV. That's our answer right there. Well, we're at a good day. The utility's not getting bogged down. It's supposed to be getting us somewhere around 13.8. It's actually running a little bit high. If it went, might even be higher because the utility plan for everybody to be loaded down, and then suddenly a bunch of solar panels next door started taking load off of them, and they got to deal with this problem. So maybe they got to bring that voltage down. But anyway, that's what we've got here. Now the next final thing is what's S. Well, we can just simply take the quantities. We could just say square root of 3 times the V feeder times the I line that we have. So that would be square root of 3 times 14.4 e to the 3 times the current, remember, was 64. So the load, total load seen by the feeder is 1.6 MVA. And there you have it. Notice that that power load is another check. It's lower than the transformer rating. So again, things are lining up pretty well here. there's just one last point I want to make. You won't always have the problem done in the same order. So please do not think that just because I've given this example several times where we worked from the load back to the feeder, that's the only way you solve problems. That's really not what engineers do. Engineers are not, when you're an engineer, you're not going to go get your first job and it's going to be executing step by step exactly what you saw in a homework problem. If you're, I had a student once complain about this severely because he didn't pass his qualifier, but he goes into a qualifier trying to get a PhD, and all the problems didn't line up with the exact sequence of what that you studied in your undergraduate classes. I'll just show you an example and just think about it, okay? Think about this. This is a real world problem example. Here's a community over here. And that community is fed by a substation. And this community has it is remote. It's a rural area. Okay, so it's rural. It's a long ways away from the nearest power generation station. It is going to be what we typically call fed by a weak grid. Big problem that utilities face, and it's aggravated by renewable energies being put on the grid, just because the way that we do renewable energies, there's better ways to do them that could actually solve this weak grid problem. But everybody wants to be conventional, and they want to use conventional distribution, and so they end up with weak grids. And here's what I'm talking about. So at the substation, you're going to have a transformer. It's probably a Wye-Delta because it's a big step down. There's a big transmission line. So your typical feed right here might be something like, let's say, 24 kV is your nominal. That's what you're hoping to get, right? Nominal feed. That would be the transformer secondary rating. It's probably got something like a 500 kV nominal on the primary. So that's really saying a 500 to 24 ratio. And then you've got a big long transmission line coming at you here. At the other end of the transmission line, you might have multiple feeds. That's the way our world is right now because we're starting to introduce a lot of renewables into the grid, for example. And let's say the utilities are owning these utilities are owning the renewables. So you've got a power plant, conventional coal plant or something like that. There's going to be a delta Y transformer coming off of a generator, probably rated around maybe also 24 kV. That's kind of pushing the limits of what generators can do from an insulation standpoint. So you've got go in the other direction, 24 to 500, trying to get a nice big voltage up. They'll probably run this generator they want to run it as high as they can so everybody can get their voltage, but they also have to recognize that there's probably other communities nearby that have a similar substation rating. And this is really a load, thinking of this as a load here, and there's a load here. If this voltage at this point here, it should be less than, say, 25 kV, because if it gets much higher, everybody's going to have their electrical systems blow up. You know, the utilities have a real challenge. They've got to make sure everybody gets their power and they get the voltage they need, and it doesn't go too high and it doesn't go too low. And now you've got this big wind farm that's also feeding into the grid. So here's your wind farm here, and everybody here wants to be green, right? And they say we want to have, we want wind power, so we can be sensitive to our environment in this world and reduce our carbon emissions. And these guys say, yeah, we're going to be good citizens if we want wind also. So they both want to get this wind power coming to them. Here's your wind generator, your wind turbine feeding your power, probably something around 4.2 kV. It's a lower power rating. If you think about power ratings for just a moment, this big generation plant, I could be way off here, but let's just say it's going to give us about let's say 50 MVA. That might be small. The wind generator can give me 5 MVA, so I've got extra power that I can get from this wind here that I want to get over to everybody else. We're going to say this isn't a big city. I think these are probably low power ratings. In fact, I'm going to go backwards. I'm going to say 550 instead. I'm going to multiply everything by 10. 500 MVA and 50. Maybe I'm on the high end now, and let's say that what this guy needs over here is, his requirement is he should have probably at least 25 MVA. That's what he wants to get. And this bigger, closer in area here has more power. They're going to want to have at least 50 MVA. And of course this is way bigger, but I'm kind of setting this up for this scenario. What happens if we were going to just lose our connection to the generation? Let's say we that for some reason the things happen so that this it goes away, or that power, you're just using the wind power for some reason. So this is a typical problem. I was just kind of setting it up, and I'm saying, okay, we've got a 50 MVA wind turbine that he should be able to give 25 MVA over here, and he should maybe be able to give this guy at least half of what he needs. So when this happens, he could, let's say, be conservative he never really needs more than 20 MVA here. He maybe never needs more than 20 MVA here. So that's what he's actually working with. So you say, here's another way to look at a problem. I just want you to think about this, and maybe you can make up your own homework problem this way. 50 MVA is all of that power is being supplied. All of the 4.2 kV is being supplied from the source side. So we're talking about, and we have this transformer that is a 4.2 to 500 step up to get this power out to everybody. And this has an impedance that's quite large because it's a very long ways out from everybody. And let's rate it on per unit. So you could say, well, I'm going to per unitize to the 500 kV side of everything. You know, we could even use the S. So we could use the S equals 500 MVA if we wanted to base it on this transformer. And it's 500 kV. And I haven't figured out what the numbers ought to be, but this would be some per unit here that's significant compared to this other one here. So I could call this per unit 2, and that could be per unit 1. So you might say, okay, if I've got this much power coming out, I know the base, it's been defined at this point right here. I can find these values here. And the question you'll ask yourself is, if these guys are loaded down here, you can just look at one of them and not both of them. I think it becomes more of a power systems problem if you look at this guy and this guy. But let's just say you're not even worrying about this guy, and the thing that you want to know is the voltage here. So this is working it from the other end. I just want to show you an example. All these problems do not get worked from load to source. They could be going the other direction. This isn't a power class, but this is where we're really teaching you the rudiments of the components that are used, principally motors and generators, but very much we have to talk about the transformer as this intermediate thing that we have to be concerned about. Anyway, that's all I've got to say. I apologize that this went as long as a full class, but I want to give you all the information that you need.